Hi dear all, we are going to explain quantum theory and other developments in this section. Actually, the quantum theory was developed to explain the black body radiation. A perfect black body is one that can absorb and emit all the radiations falling on it. So, a perfect black body is not available, but carbon black is nearing a black body. Now we are going to explain quantum theory and explanation of the black body radiations. Okay. Quantum theory. Classical wave theory fails to explain the following phenomena. One, photoelectric effect. Two, black body radiation. Third one is, it fails to explain the variation of heat capacity of solids, variation of heat capacity of solids with the temperature. Fourth point is, it fails to explain the origin of hydrogen spectrum. These phenomena show that the system absorb or emit radiations in a discrete manner. This could not be explained by classical wave theory. In order to explain black body radiation, Max Planck suggested the quantum theory. The intensity of the black body radiation changes with a change in temperature. When intensity of the black body radiation values are plotted against wavelengths, the following graphs are obtained. This graph is obtained at T1 temperature, and this graph is obtained at T2 temperature. T2 is greater than T1. From the graph, it is clear that the intensity of the black body radiation increases with an increase in wavelength at first and then decreases at a constant temperature. As temperature increases, the intensity of the black body radiation increases. See, this is the intensity. This curve stands for the intensity of the black body radiation at a lower temperature, and this curve stands for the intensity of black body radiation at a higher temperature. Moreover, see, this is the maximum in the intensity at T1 temperature, that is at lower temperature. When a tie line is drawn to the wavelength axis, at point A, corresponding wavelength is obtained. But if the maximum in the intensity at higher temperature T2 is considered. It will be at this point when a tri-line is drawn. When a line is drawn to wavelength axis, it meet at a point B. From this it is clear that as temperature increases, the maximum in the intensity of black body radiation will be shifted to lower wavelength region. See, B is the lower wavelength region. This property or this phenomenon cannot be explained by the classical wave theory. In order to explain this, Max Planck suggested that the absorption or emission of radiations takes place due to the oscillators or atoms in the surface of the black body. Oscillators or atoms in the surface of the black body. That is, these atoms on the surface of the black body are responsible for the absorption and emission of the radiations. And the change in intensity of the black body radiation is due to the interaction of these oscillators with the oscillators present in the radiations. From this, Max Planck suggested that the absorption or emission of radiations from an atom or a molecule take place in a discontinuous manner, not in a continuous manner. That is, absorption or emission of radiations takes place in discrete packets. Discrete packets. These packets are called quanta. And each packet is called quantum. Quantum is singular and quanta is plural. That is, the absorption or emission of radiations takes place in discrete chunks of energy. He derived an expression for a quantum of energy as E is equal to h into nu, h nu. Here E stands for a quantum of energy. H stands for Planck's constant. And nu stands for frequency of radiation. Since nu is equal to c by lambda, we can substitute the value of nu here. We get E is equal to hc by lambda. This is the relationship by which a quantum of energy is expressed in terms of wavelength. This is the expression by which a quantum of energy is expressed in terms of frequency. Therefore, Max Planck explained the energy of radiations in terms of small packets that may change with the change in temperature as a function of frequency or wavelengths. Quantum theory can be explained by comparing with a standing staircase. If we consider a standing staircase, a person can stand only in a step and not between the steps. That is, the absorption or emission of radiations takes place as integral multiples of h nu, that is n into h nu, where n is an integer like 1, 2, 3, 4, etc. That is, the quantum of energy takes the value 1 into h nu, 2 into h nu, 3 into h nu, and so on. Never it takes the value between these values, or it could not take a fractional value. Actually, this quantum theory helped Niels Bohr to introduce a new model of atom. Photoelectric effect. When light is allowed to fall on the surface of certain metals like potassium, cesium, etc., electrons are ejected from their surface. This phenomenon of ejection of electrons from the surface of the metal by the incidence of light is called photoelectric effect. This phenomenon was discovered by Hertz. See, a vacuum tube is taken and there is a metal like potassium, cesium, or any other photoelectric substance. It acts as cathode, and there is a collector. This acts as anode. When light is allowed to fall on the surface of the metal, see, from the surface, electrons are ejected. This process of ejection of electrons by the incidence of light is called photoelectric effect. Important characteristics of photoelectric effect are the following. 1. Photoelectric effect is instantaneous. That is, the ejection of electrons takes place only at the time of incidence of the light. It will not continue when the incident light is cut. It takes place only at the time of falling light on the surface. 2. Number of electrons ejected is directly proportional to intensity of falling light. That is, when bright light fall on the metal surface, the number of electrons ejected will be high. But when diffused light fall on the surface, the number of electrons ejected will be less. Then third point is this. Kinetic energy of the ejected electrons, or EK, kinetic energy of the ejected electrons, is directly proportional to the frequency of falling light. Frequency of falling light. That is, as the frequency increases, the kinetic energy increases. Fourth point. A minimum frequency is required. A minimum frequency is required to just start the ejection of electrons. This minimum frequency is called threshold frequency. Threshold frequency. That is, if the threshold frequency of a metal is 90, the radiation of 89.9 Hertz frequency cannot start the ejection of electrons, and only at 90 the electron ejection starts. That is why we say a minimum frequency is required to just start the ejection of electrons, and this minimum frequency is called threshold frequency. Every metal has a threshold frequency. The phenomenon photoelectric effect was explained by Albert Einstein. Based on quantum theory, or with the help of quantum theory. According to quantum theory, falling light contains a large number of discrete packets of energy called photons. Each photon is associated with a quantum of energy. So, the energy of falling photon is expressed as h nu. See, on the surface of the metal, there are atoms, and electrons are revolving around the nucleus like this. There is a force of attraction between nucleus and electron. One part of the energy of the falling photon, that is, falling photon has the energy h nu. One part of the energy of the falling photon is used to break the force of attraction between nucleus and the electrons, and the remaining part or rest part of the energy of the falling photon is given to the electron as kinetic energy. See, one part of the energy of the falling photon is used to break the force of attraction between nucleus and electrons. That is why ejection of electron takes place, and the rest part is given to the electron as its kinetic energy. The energy that is given to break the force of attraction between nucleus and electron is called threshold energy or work function, and it is expressed as W0, and its energy is h nu 0. That is the minimum energy required to break the force of attraction between nucleus and electron. Therefore, keeping the law of conservation of energy in mind, we can say that energy of falling photon is equal to work function, that is the minimum energy required to break the force of attraction between nucleus and electron, plus kinetic energy of the ejected electrons. The energy of falling photon is h nu is equal to W0 plus kinetic energy. And we know that h nu is equal to h nu 0 plus kinetic energy. Therefore, kinetic energy is equal to h nu minus h nu 0. h nu minus h nu 0. Or we can say that kinetic energy is equal to h into nu minus nu 0. That is, kinetic energy is equal to h into delta nu. Kinetic energy is expressed as mv square by 2 or half mv square, that is mv square by 2 is equal to h into delta nu. See, this is m is the mass of electron, v is the velocity of the electron, h is the Planck's constant, and delta nu is the change in frequency, that is difference in frequency between the incident frequency and the threshold frequency. Okay. This is the explanation for the photoelectric effect. See, each falling photon is responsible for the ejection of each electron. So, photoelectric effect supports the particle nature of light. Okay. Let us learn the classification of spectrum. Spectrum is an ordered arrangement of electromagnetic radiations according to their frequency or wavelengths. The instrument that is used for making spectrum or taking spectrum is called spectroscope. It consists of a prism or grating to disperse the radiations falling on it from a source, and then the dispersed radiations are allowed to fall on a photographic plate or detector. The picture or the lines obtained in the photographic plate or detector is called a spectrum. Spectra are widely classified into emission spectra and absorption spectra. Emission spectra and absorption spectra. Emission spectrum is due to the electromagnetic radiations already absorbed by the atoms or molecules in the substance. Emission spectrum is widely classified into continuous spectrum and line spectrum or line emission spectrum. See, emission spectrum is widely classified into continuous spectrum and line spectrum. Now we are going to explain continuous spectrum. When white light is allowed to pass or allowed to fall a prism in a spectroscope, it gets dispersed into 7 colors. If these 7 colored lights are allowed to fall on a photographic plate, we get a continuum of colors, a continuum of colors in the spectrum. Thus obtained spectrum is called continuous spectrum. Here, red light with a very long wavelength is deviated to a small extent, and violet with a very short wavelength is deviated to a larger extent. In this spectrum, violet merges in indigo, then indigo merges in blue, and so there is no gap between the colors, constituent colors in this spectrum. That is why the spectrum is called continuous spectrum. Now let us learn what is line spectrum. When a metal or a metal salt is shown to a flame, metal or metal salt is shown to a flame, corresponding colored light is produced. Similarly, when gases are subjected to electric discharge, when a gas is subjected to electric discharge in a discharge tube, corresponding colored light is produced. If this colored light is passed through a prism, that is, the light obtained by burning the metal or metal salt or by the discharge of the electric discharge of the gases, is passed through a prism in a spectroscope or spectrometer, the ray get dispersed, and we get colored lines with a dark spacings between them in the photographic plate. In the photographic plate, we get colored lines with a dark spacing between them. Thus obtained spectrum is called line spectrum or line emission spectrum. See, I am going to explain how is a line in the line spectrum obtained. See, when an atom is considered, the electron may be present in a particular energy level. See, there is an electron in the first level. If the metal is burned or salt is burnt or gas is subject to electric discharge, some energy is supplied. This electron may absorb that energy and jump up to a higher energy level. This depends on the amount of the energy absorbed by it. If it absorbs low energy, it may jump up to a second level. If it absorbs higher energy, it may jump up to a higher energy level. But these energy states are called excited states and they are highly unstable. So the electron may jump down to the lower energy level. It may jump down to the lower energy level by losing energy in the form of electromagnetic radiation, EMR. This electron also jump down to the lower energy level by losing energy in the form of electromagnetic radiation of another wavelength. This electromagnetic radiation emitted by the excitation followed by de-excitation. Excitation of the electron followed by de-excitation is the cause of the lines in the line spectrum. So the lines in a line spectra is due to the electromagnetic radiations emitted when an electron undergo excitation followed by de-excitation. Now, since this spectrum is obtained or the lines in the spectra is obtained from atoms, it is called atomic spectrum. Line spectrum is actually the characteristic of a particular atom, hence it is considered as the fingerprint of an atom. It is considered as the fingerprint of the atom. Now let us learn what is absorption spectrum. See, a sample of substance is taken in the form of gas or solution in a chamber. A gaseous substance or solution containing the substance is taken in a chamber, glass chamber. Now radiations having different radiations of different wavelengths is passed through the substance and then allowed to pass through a spectroscope. The radiations, dispersed radiations are then allowed to fall on a photographic plate so that alternate bright and dark bands are produced in the photographic plate. Thus obtained spectrum is called absorption spectrum. The dark lines are due to the absorption of corresponding wavelength of the incident light by the substance present in the gas or solution. Absorption spectrum is used to identify a compound or substance. Therefore, absorption spectrum is widely used in analytical chemistry. It can also be used even to identify the impurities present in the sample. That is, when pure sample is used, one particular absorption spectrum is obtained, but when impure sample is used, the spectrum will be different. Therefore, it is possible to check the purity of a sample from analyzing absorption spectrum. We can do a problem. Question. Calculate the frequency and wave number of a radiation of wavelength 600 angstrom units. See, we are asked to find the frequency and wave number of a radiation of wavelength 6000 angstrom unit. 6000 angstrom unit. First of all, we can calculate the frequency. We know that nu is equal to C by lambda. Now, data. Velocity of light c is equal to 3 into 10 raised to 8 meter per second. And lambda is given. Lambda is equal to 6000 into 10 raised to minus 10 meter. 1 angstrom unit is equal to 10 raised to minus 10 meter. That is the conversion. Substituting here, we get 3 into 10 raised to 8 meter per second divided by 6000 into 10 raised to minus 10 meter. Meter getting cancelled off. We get 3 into 10 raised to 8 divided by, say this is 6 into 10 raised to minus 7. See, this is 6 into 10 cube. 10 cube into 10 raised to minus 10 is equal to 10 raised to minus 7. That is why we wrote it as 6 into 10 raised to minus 7. That is equal to 3 by 6 into 10 raised to 15. 10 to the power minus 7 comes in the numerator as 10 raised to 7. 10 raised to 8 into 10 raised to 7 is equal to 10 raised to 15. And you know this is 1 by 2. 1 by 2 is equal to 0.5 into 10 raised to 0.5 into 10 raised to 15. That is 5 into 10 raised to 14 per second. See, a second remains second inverse here. Here it's also second inverse, second inverse. That is 5 into 10 raised to 14 will be the frequency of the radiation. Now, we are asked to calculate the wave number. Nu bar is equal to 1 by lambda. And we know that lambda is 1 by 6000 into 10 raised to minus 10 meter. See, this is 1 by 6 into 10 raised to minus 7 meter inverse. That is equal to 1 by 6 into 10 raised to 7 meter inverse. That is equal to 0.167 into 10 raised to 7 meter inverse. That is nu bar is equal to 1.67 into 10 raised to 6 meter inverse. That will be the wave number of the radiation. So this is the frequency of the radiation and this is the wave number of the radiation. That's it. Now another problem. A 100-watt bulb emits a monochromatic light of wavelengths 400 nanometer. Calculate the number of photons emitted by the bulb per second. Say, question is, a 100-watt bulb emit a monochromatic light, means a single colored light of wavelength 400 nanometer. We are asked to calculate the number of photons emitted by the bulb in 1 second. See, power of bulb is 100 watt, means 100 joule per second. Now let us calculate the energy of a photon. See, energy of a photon can be calculated using the formula E is equal to hc by lambda. E is equal to h nu, nu is equal to c by lambda, so E is equal to hc by lambda. We can use data here. See, h, Planck's constant is 6.626 into 10 raised to minus 34 joule second. C is velocity of light, 3 into 10 raised to 8 meter per second. Now lambda is the wavelength of the monochromatic light emitted by the bulb, that is 400 nanometer, that is 400 into 10 raised to minus 9 meter. Substituting the values here, we get 6.626 into 10 raised to minus 34 joule second into 3 into 10 raised to 8 meter per second, the whole divided by wavelength is, or lambda is 400 into 10 raised to minus 9 meter. See, meter getting cancelled off, second and second inverse getting cancelled off, we get 6.626 into 3 into 10 raised to minus 34 into 10 raised to 8 divided by 400 into 10 raised to minus 9. See, this is 0.0496 into 10 raised to, see, minus 9, 10 raised to minus 9 comes in the numerator as 10 raised to plus 9. 10 raised to 8 into 10 raised to plus 9 is equal to 10 raised to 17. Now 10 raised to minus 34 into 10 raised to 17 is equal to 10 raised to minus 17. See, this is 10 raised to minus 17. Remaining unit is joule. That is, see, displacing or expressing this value in scientific notation, it's given as 4.96 into 10 to the power minus 19. See, we are displacing this decimal point after 4 by multiplying with the 10 square. Without changing value, we have to divide with the 10 square. That 10 square comes in the numerator as 10 raised to minus 2. So 10 raised to minus 17 into 10 raised to minus 2 is equal to 10 raised to minus 19 joules. That's the value of energy of a photon, means a quantum of energy. Now we can calculate the number of photons emitted, by dividing the power of the bulb by the energy of a photon. So power of the bulb by energy of a photon, that is equal to, the power of the bulb is 100 joule per second. Energy of a photon is 4.96 into 10 raised to minus 19 joules. Joule getting cancelled off. See, 100 means 10 square. That is 1 into 10 square divided by 4.96 into 10 raised to minus 19. That is equal to, see, 10 raised to minus 19 comes in the numerator as 10 raised to plus 19 into 10 raised to 2 is equal to 10 raised to 21. Therefore, 1 by 4.96 into 10 raised to 21 per second. See, therefore, number of photons emitted is equal to, 1 by 4.96 is equal to 0.2016. 1 by 4.96 is equal to 0.2016 into 10 raised to 21 per second. That is equal to, expressing in scientific notation, 2.016 into 10 to the power 20 per second. That is 2.016 into 10 raised to 20 photons were emitted from the bulb per second. That's all. Another question. Threshold frequency of a metal is 7 into 10 raised to 14 per second. Calculate kinetic energy of electron ejected when frequency of radiation 1 into 10 raised to 15 per second fall on the metal. So I am going to repeat the question. The threshold frequency of the metal is 7 into 10 raised to 14 per second. We are asked to calculate the kinetic energy of the electron when a radiation of frequency 1 into 10 raised to 15 per second strike or fall on the metal. Now we can apply the theory or principle of photoelectric effect here. Kinetic energy of the ejected electron EK is equal to H into nu minus nu zero. Data given in the problem. H is 6.626 into 10 raised to minus 34 joule second, that we know. It's a constant. Nu is the frequency of the falling radiation, that is 1 into 10 raised to 15 per second overheads. Nu zero is the threshold frequency. It is 7 into 10 raised to 14 per second overheads. Substituting the values here in this expression, we get 6.626 into 10 raised to minus 34, that is H, into nu is 1 into 10 raised to 15 and nu zero is 7 into 10 raised to 14. That is equal to 6.626 into 10 raised to minus 34 into, see, taking 10 from 10 raised to 15 and multiplying with 1 to get 10 into 10 raised to 14 minus 7 into 10 raised to 14. That is 6.626 into 10 raised to minus 34 into 10 minus 7 into 10 raised to 14. 10 raised to 14 is taken outside as common factor. That is 6.626 into 10 minus 7 is equal to 3 into 10 to the power minus 34 into 10 raised to 14. That is 6.626 into 3 into 10 raised to minus 20. That is 6.626 into 3 is equal to 19.2 87 into 10 raised to minus 20. Converting it into scientific notation, we get 1.987 into 10 raised to minus 19. By shifting one decimal to left, we can take 110 from here. This 10 raised to minus 20 into 10 raised to 1 is equal to 10 raised to minus 19. Therefore, kinetic energy is equal to 1.987 into 10 raised to minus 19 joules. This is the kinetic energy of the ejected electron when a radiation of frequency 1 into 10 raised to 15 fall on the metal. That's all.